sitting right on my desk there. All right, so game plan for today. We are going to go over section 4 notes. The worksheet we did Friday. What we will do tomorrow. There's another set of in-class problems associated with this section. What we'll do is both of those worksheets tomorrow. So both worksheets will be turned in and looked at tomorrow. You'll have plenty of time. This section, it won't take all class period, but I do want to get all the notes in because your test is Friday. Okay? Now, any questions before we get going with notes here? Okay, so here we go with our notes. Yes, sorry. Notes. Hang on. All right, so what we've talked about so far, average rate, collision theory. We've talked about what makes a rate go faster or slower, or a reaction go faster or slower. And then we've talked about rate loss. What we get into now is our instantaneous rate. So an instantaneous rate is saying at a specific time, what is the rate? By definition, remember, reactants are going to decrease as the reaction progresses. An instantaneous rate, by definition, is found from the tangent of this curved line. Now, we are never going to have to take the tangent of the curved line. We're not ever going to have to take, in this class, and find the particular slope of that line. But, by definition, that's where we find or get our instantaneous rate. So we go through this. Great. We have an instantaneous rate. We need to utilize the rate law, and then from there, all we have to do is plug numbers in. So rate law is the stuff we have been doing. We're not going to take the time to go through it like we have. I'm typically going to give it to you in word form, and you will have to plug these numbers in. Questions?
Do you know what his tissues are?
Paper towel is the best thing I got here. So here's our example problem. It says in this equation, hydrogen H2 is first order, and nitrogen in the actual black container there, if you push on the handle, and nitrogen monoxide, NO, it is second order. We also are given the rate constant, K. So first priority we have to do is write out the rate law. Now, before we took time and we looked at experiments and did all this stuff, now all we have to do is this. We just say rate equals K times the first substance, which is H2. So I'm going to put that in brackets. Now, it is first order, so we would raise it to what power? 1. Do we write the 1?
No.
Okay, so we leave it here. Now, next substance is NO, so we put nitrogen monoxide in brackets. It is second order, so what power do we put it to? We raise it to that second power. So we have the rate law. Now all we have to do is plug these numbers in. And just so you know, this 2.9 times 10 to the second is our K for our constant in this specific equation. So here we go. Our rate is equal to our K, which I'm going to insert here as 2.90 times 10 to the second. The unit on this is m to the minus 2, s to the minus 1. And because it's in scientific notation, I'm going to go ahead and take the time to put it in parentheses. I will then multiply it by the concentration of H2. So if we look down here, H2 has the concentration of 0.004. So I'm going to say times the concentration of 0.004. It's raised to the first power, so I don't really need to worry about the power in this situation. And then I multiply it by the concentration of nitrogen monoxide. So I say times, and I put the concentration 0.002, but with NO, we have to raise it to that second power. So what you would need to do if you tried to calculate this is put it in as rate equals, parenthesis, 2.9 times 10 to the second, close the parenthesis, times 0.04 times parenthesis 0.002 square, and then I would close the parenthesis. When you do that, I guess I should ask first, is anybody wanting to try to calculate it before I give you the answer? Good. All right. When you do this, you get an answer. In scientific notation, our rate is equal to 4.64 times 10 to the negative 6. And I'll ask you this. What unit should our rate be in?
M negative 2s negative 1.
Not quite. M per your unit time, which our time is s per second. So m/seconds. Questions? Bottom line here, find your rate law, which is typically given in Word format, plug numbers in. Any questions? Does anybody still need this? Good. All right, moving on to our reaction mechanisms. Reaction mechanisms. If we think back to collision theory says, hey, reactants have to smack each other with enough force and be orientated in the proper direction. However, chemical equations, chemical reactions are a little bit more complicated than that. So what these are a proposal of a set of steps that get us to the overall reaction of interest. So it combines some things that we talked about in chapter 16, Hess's law, and it's almost like a proof in geometry where we're saying, okay, bottom line, we want to get to this, prove how this exactly happens, okay? Questions? In a reaction mechanism, we're going to have two things, or typically have two things. One is an intermediate, which is formed in one step, used in another. The other is a catalyst, which is shown in one step and then later produced in an additional step. But both of these things are not in the overall equation. So check this out. Chlorine, Cl. Chlorine, Cl, we start with it. Then in equation 3, or step 3, we produce it. Because we start with it in one reaction, and we later produce it, that is known as a catalyst. ClO, on the other hand, it's produced one step, then used in a later step. That is known as an intermediate. Questions? All right. The final thing is this. The rate determining step is the slowest step, and it also defines or limits what our rate law can be. Okay? Questions? Let's do 2 examples, and then we'll be good to go with section 4. So ultimately, we want to know what series of steps could possibly tell us what happens when nitrous dioxide or dinitrogen monoxide decomposes. So here's our series of steps. So the first thing that we have to do is verify that what we want shows up in our overall reaction. So what we have to do is this. We have to add our equations together. Very similar to Hess's law. Now, Hess's law said items that are on opposite sides of different equations can be crossed out. Those are similar items. So we start with this. The first thing that I recognize that can be crossed out is O for oxygen. It is on the right-hand side of that first equation and the left-hand side of that bottom equation. Now, it is produced in one step, used in a later step. So, those things right there, oxygen is known as an intermediate. We double check ourselves and say, okay, there is nothing else on opposite sides of the different equations that can be crossed out. So we add these together. So we have N2O plus N2O, so that gives us a total of 2 dinitrogen monoxides on that left-hand side. Now, there is nothing else left on that left-hand side, so we draw our arrow, and then we have this. Nitrogen N2 plus another nitrogen N2 gives us 2 N2. And then we have one more substance that's just an O2 of oxygen. There's only one of them, so we write down O2. Now, this is what we want to have happen. We also need to check, hey, is this really a balanced chemical equation when we add these two steps together? Check, it is. And so this right here that I just boxed in blue is known as the overall reaction. And I'm going to abbreviate reaction as RXN. So this is our verification. Yes, this could be a set of steps. That's what this is saying. Now we get to our rate law. Our rate law is determined by our slowest step. So we can start out and say rate equals K. Which one is our slowest step? Step 1 up top or step 2 down below?
Step 1.
Step 1.
Yes.
Now, if step 1 is the rate determining step or the slowest step, all we need to do with just the slowest step is cross out or blank out our products. We are only looking at our reactants. The only reactant here is N2O. So we'll have next to our K, N2O, and then for this process, this is the only time in a rate law that we look to our coefficients in that slow step to identify what power we have. So we go in front of N2O, just the slowest step, and what is that coefficient in front of N2O? 1. Now, typically we don't put 1 as the coefficient or 1 as the power, but to show you where that came from, I did want to write that down for this one. So that would be our rate law. It comes from our slowest step. Because the first step was our slowest, we can go ahead and write that down. Now we have this. We need to write our reaction diagram. So our reaction diagram would look like this. On the X, or the left to right axis, would be what we call reaction progress. On the up and down axis, this would be how much energy is in each of those processes, where the bottom is low energy, top is high energy. Then we have this. Each step is going to be represented on our diagram by that hill. That's showing that there's an additional step. The biggest or the largest hill comes from our slowest step, which is also going to require the most energy. So step 1 is the slowest. What we do is this. Because step 1 is the slowest, we draw a really giant hill. Then step 2, it's a really fast step, which means it does not require as much energy. And so we would have something that looked like this. Again, biggest hill is the slowest step. It requires the most energy. Smaller hill, which is hill number 2, is a really fast step because it does not need much activation energy. Okay? Questions? Now, this whole thing would be confirmed via an experiment. Remember, rate laws are determined via an experiment. So we would have to say, hey, yep, check, this thing does check out. This is a possible way that we could get from our reactants down to our products. Questions? Does anybody need this? Okay, one more equation. I throw a little bit more complicated process. Our slow step's going to be in the middle. This time we want a reaction between nitrogen monoxide and H2 hydrogen gas. So first step is we need to add these things together to give us our overall equation. Now, we got to cross out the intermediates in the catalyst. Somebody yell out one thing that can be crossed out.
N2O.
N2O. All right, N2O is produced in that middle step, used later in the final step. It's known as an intermediate. There's one more item that can be crossed out. Yep, N2O2. Again, it is an intermediate because it's produced in that first step, used in the second step. Now we just add everything together. So when we add everything together, we get 2NO plus H2 plus H2 is 2H2. This produces H2O plus H2O, so 2H2O plus R N2 for nitrogen gas. Now, again, we would confirm that, hey, this is balanced. We would also say, this is what we want. We want this stuff to start out, our reactants, and our products to look exactly like this and be balanced exactly like this. Well, it checks out, so yep, this could be a set of steps that leads to our overall reaction. We write the rate law, except this time we can start still with rate equals K, but our slow step is right in the middle. Now, what has to be done if you have a scenario like this where your slow step is actually in the middle, it's like going through or trying to get through 3 stoplights. You get through the first one, but the second stoplight you get stopped at. So to find the rate, it's a combination of that total distance between those stoplights that you went through and then got stopped. Now, so I'm going to start out with this. I'm going to say rate equals NO because it's the reactant of that fast equation up top. NO has what coefficient and what power do we need to raise that to? 2. So we raise it to the second power. Then I'm going to put H2 in brackets. It has a coefficient of 1. So I'm going to leave it with no written power. We assume that's 1. And somebody tell me why I am not going to write N2O2 into my rate law.
It's crossed out.
It's crossed out, number 1, and it's an intermediate in those set of steps. The other thing is this. If you look at our final equation, N2O2 has nothing to do with our final equation. So it's another check or verification that, hey, this is in fact possible or true. Last thing is our reaction mechanism. So again, we have reaction progress and we have our energy. So this time we have 3 steps. So how many hills will we have in our diagram? 3. What is going to be the steepest hill?
The middle one.
There we go. So hill, little hill, huge hill for our large activation energy, and then another little hill for that fast step. Biggest amount of energy, or biggest or highest activation energy, is our slowest step. Any questions? Okay.